Hello and welcome back to Algebra 2. Today we are looking at a new topic called logarithm. So the idea here is actually just kind of relating to what we did in past. How to solve for exponential equations where you do not have a same base or where you cannot get a common base. So meaning, how would you solve for something like this? If you have, like, say 4 to the x is equal to 7. So notice that the 7, I cannot rewrite that as 4 to the something, nor can I write 4 as 7 to the something. So how do you get a common base then to solve for this? So this is where the idea of logarithm actually comes in. So first off, we need to define what is a logarithm so you can see how that actually works. So the definition, the formal definition is that the log of a is equal to x means the same thing as a is equal to 10 to the x. So just cleaning that up, let me show you what I mean. So if I were to say log of 2, right? If I were to say log of 2, that is basically saying, hey, 10 to what power is equal to 2? Okay, so when you say log of 2, that's the equivalent of saying 10 to what power is equal to 2. Now, something like this, you cannot solve for by hand because it's just way too hard. So this is where your calculator actually comes in. So you're going to take this log of 2 and plug it into your calculator, and you're going to get a numerical answer for this. And if I remember correctly, the numerical answer, which is going to be approximately 0.301. So in conclusion, log of 2, meaning 10 raised to what power is equal to 2, is equivalent to 0.301. Now here, let me just go to the calculator so you can see that for yourself. So I'm going to go to quit. So as we said, log of 2 is going to be equal to 0.301 approximately. So if I take 10 raised to the power of 0.301, then that should approximately give me 2 as an answer, and there you go. If I put that exact answer in there, then I would get the exact value of 2, but log of 2 is what they call an irrational number, meaning that you cannot write this as a fraction, so therefore there's no finite, you can't plug a number, you can't plug an irrational number in there in order to get something that's nice and clean. You have to actually round off. Okay, so just to give another example, if I were to say what is the log of 7, then by definition, that's like saying 10 to what power is equal to 7. So again, this is where you can go ahead and plug into your calculator and figure that one out. And if I remember this one correctly, this is going to be approximately equal to 0.845 if memory serves me correctly. So let's just go ahead and check that one more time. So let's see, log of 7. So that's going to be 0.845. Hey, I'm pretty good at this, hopefully. So 10 raised to the power of 0.845. So that is going to be 6.998, which, yeah, that's pretty close to 7 then, okay? All right, so now what we can do is use this definition of logarithm to help us solve for some of these exponent problems. So here in the first one, let's say I want to solve for 10 to the x is equal to 5. Well, by our definition of logarithm, then that means that x is equal to the log of 5, and that's what we're going to be putting into the calculator. So at this point, you just go ahead and put log of 5 into the calculator to see what it comes out to be. And if I remember correctly, that's going to be equal to 0.477 then. So that's going to be our answer. So all of these problems that we're doing right here, unfortunately, you're going to have to use a calculator for it. But hey, at least we're solving for these numerical values then somehow. On to the next one. If I have 10 to the x is equal to 1.1, then we're going to go ahead and use a calculator to solve for it. But before we do so, we have to tell the calculator what to plug in. The plug-in, according to our definition of logarithm, is x is equal to the log of 1.1. Unfortunately, that's something I do not know, so we're going to go ahead and put that in the calculator to see what that is. So here, we're going to go ahead and say log of 1.1, and that comes out to be 0.041. So that is going to be our answer then. So 0.041. So once again, that means that if you take 10 raised to the power of 0.041, that should approximately give you that 1.1 that you're looking for. So that's our answer here, and that's our answer here. Not too bad, hopefully, right? Keep moving along over here. Let's say that there's a 4 in the front, and let's just go ahead and make the exponent a little bit more complex. But still, you know, this one isn't too much of a problem because it's just a matter of order of operation. First, we're going to get rid of the 4 that is in the front by dividing. So 10 raised to the power of x minus 1 is equal to 3 divided by 4, or you can say 0.75. Now we can go ahead and use the logarithm property, or the, sorry, not property, but the logarithm definition to get x minus 1, the exponent, is equal to the log of 3/4. And finally, if I want to solve for x, then that means that x is equal to 1 plus the log of 3/4. And you'll note that I actually don't write it as log of 3/4 plus 1 because this right here could be a little confusing to people. Some people might think that it's the log of 3/4 plus 1 where 1 is inside the logarithm. And I don't like that because, that's kind of ambiguous. So rather than that happening, I write the 1 in front. So then that way we can just be very clear as to what we're solving for. So take that guy and put it into the calculator. So let's see here. We have 1 plus the log of 0.75. So the answer is equal to 0.875 then. Okay. So this is approximately equal to 0.875. And finally, for this last one right here with the base 10 of x is equal to -3, that right there is actually a trick question because the problem is when you have an exponent right here, right, you think about how exponent works. There's no exponent that I can give you or you can give me where the result when it's 10 to the raised to that power is equal to a negative number. So what that means is there's no solution for this because this is not solvable. While it is true that you can write it as x is equal to the log of -3, that right there is going to blow up on you because if you try to put that in a calculator, it doesn't work. So in conclusion, what that means is for our definition of logarithm, we can be a little bit more specific. We have to make sure that a is a number that is greater than 0. So this only works if that is true, because if it isn't, then we can't actually solve for it then. Okay. All right. Now, going back to our original question, well, how do you solve for 4 to the x is equal to 7? Because, well, it's all good and great because, if my base is 10, we can go ahead and use this logarithm thing. But what happens once again, if you have 4 as your base instead of 10 as your base? Well, what we can do is make a quick substitution. So here's what we're going to do as kind of like a sneaky step. We're going to go ahead and say let 4, which is that base, equal to 10 raised to the k power. So let 4 equal to 10 to the k power. If we go now to make that substitution in, then we're going to have 10 to the k power raised to the x power is equal to 7, going back to the original part. And hey, there you go. Look at that. We now have a base 10 that allows us to use logarithm. So 10 raised to the kx is equal to 7 because we can multiply the exponents. And so k times x is equal to the log of 7. And so therefore, x is then equal to the log of 7 divided by k. And that right there runs into a little bit of problem because, well, x is equal to log of 7, which I can find. But what is k then? Well, that's where your middle step, your substitution, comes in. According to 4 is equal to 10 to the k, then that means that k is equal to the log of 4 because of our definition. And so my final answer is going to be the log of 7 divided by the log of 4. So that I'm going to go ahead and put into your calculator then. So let's see. Let's go ahead and put that in there. Let's just see what comes up. So we have log of 7, okay? And then we have close the parentheses, divided by the log of 4, and close that parentheses. So that's 1.404. So that's going to be our answer right here. So 1.404 then. So what that means in the end is 4, if I raise it to the power of 1.404, that should give me approximately 7 as our answer. So let's just go ahead and double check. 4 raised to the power of, and let's see if we can be precise about this. We're going to go ahead and say raise it to the answer that I have because now I don't have to round it off. And if that gives me 7, then that means we're doing something right. So there you go. Okay, so here it is. And if you want, we can just go ahead and say raise it to a power of 1.404 just as a round off. It should give you something close to 7. Okay. All right. So now let's look at a second example. Let's say this time we have 3 to the x is equal to 8. Now, just going through the same procedure, I'm going to start off by saying let 3 be equal to 10 to the k. If I do so, we are going to get 10 to the kx is equal to 8. So k times x is equal to the log of 8. So x is equal to the log of 8 divided by k. And if you recall back of our substitution, k is then equal to the log of 3. So then that means our answer is going to be the log of 8 divided by the log of 3. At this point, you're probably thinking to yourself, hey, you know what? I noticed that there is a pattern, because if you look at our answer here, you'll notice that we have log of 8 divided by the log of 3. Here we have the log of 7 divided by the log of 4. So it looks like it's going to be the 7 and the 4, which are going to be these original numbers. And just like the 8 and the 3, it's going to be the original numbers. If I were to use that idea, because it seems like the math is going to be the same every single time around, I do believe that we can solve for this answer fairly quickly. If I'm looking at it correctly, then that means that this is going to be equal to the log of log of 14 divided by the log of 5. Let's try that on the calculators to see what we get. So let me go over here. Let's take the log of 14 divided by the log of 5. So that's supposed to be the numerical value. So I'm going to go back to this original problem, and I'm going to say 5 raised to that power, does that equal to 14? So let's go back to this part right here. So 5 raised to the answer, oops, not 2, but 5 raised to that answer. If it gives me 14, then it looks like I'm on the right track. And yes, it does. So there it is. So there it is. Makes it a lot easier. So here's my conclusion then. If I have x to the a is equal to b, now, according to logarithm, I am no longer restricted to having the base 10, but rather I can use any base that I want. And it turns out that x, we have kind of like derived it in a way, is going to be equal to the log of b divided by the log of a. And that right there is going to allow you to solve for x in the exponent a lot faster then. All right, thank you so much for watching. I will see you guys next time. Bye.